All right, everyone, welcome back. Now, we have seen how to take derivatives of almost every single type of function that we could come across. We saw how to take derivative of transcendental functions like sine, cosine, tangent, ln of x, e to the x. We also have seen how to take derivatives of polynomial and algebraic functions, like y equals x squared, square root of x, and so on. Now we're going to be going back to when we first defined the derivative. We defined the derivative when we first began talking about it as the rate of change of points on a graph. So, for example, take, let's say, f of c here. We want to know what's happening at this point to the slope at this particular point, and we did this by taking the derivative, finding the equation of the tangent line, and that gave us, well, the derivative gave us the slope at that particular point. So now we're gonna go back into talking a little bit more about the derivative as a rate of change. And for this particular lecture, we're going to be discussing what it means to find something that is a related rate. And from what we have seen, we will use the chain rule to find dy dx implicitly. We have seen this before. Now, another use of the chain rule is finding related rates. So another use of the chain rule is to find the rates of change of two or more variables that are changing with respect to time. With respect to time. So we're interested in finding out how these variables change as time passes. For example, it's a very common example when related rates are introduced. Think of when water is drained from a tank. In this particular example, I will use a canonical tank, but the way that I like to think about it is a tinaco. So I was born and raised in the Dominican Republic, and shortage of water is not uncommon. So in the roofs sometimes of houses, we have this big water tank that you may see in over there. We call this a tinaco. And what this does is that this stores water, either rainwater or water from the drain, so that when the water runs out, people can still shower, cook, and so on. So this water gets drained at a particular rate. So the actual tank that we're going to talk about, instead of being like this, will be more of a cone. So it'll look like this. Okay, and then in the bottom, water gets drained from here. You may have water getting drained down here. Okay, so let's say we have some water here. So when water is drained from a cone like this, so when water is drained out of a conical tank, the volume of the tank, we'll call V, capital V, the radius of the tank, called lowercase r, and the height of the tank, of the water level in the tank actually. So the height I'll call h of the water level in the tank are all functions of time t. And the reason why I chose a canonical tank is because we have an equation for the volume of such a figure. And the equation is, if you don't remember from 8th grade, is pi over 3 times r squared times h. So the volume of a cone is pi over 3 times the radius squared times the height. Now, this particular function, and in fact the difficulty of this related rates problems is finding out how the variables that you are given are related to one another. So because we are dealing with a cone, we have that the volume of the cone is precisely equal to pi over 3 times r squared times h. So this is what we will call our original function that relates all three of the variables. It relates v, little r, and h. Now, we can do the following. We could take the derivative with respect to time t. So that's the one last variable that we have not related. So we can take the derivative implicitly with respect to time t. And much like we did with the implicit differentiation of terms involving y, remember that when we took the derivative, so recall, I'll do it on this side, recall if you had something like this, like y equals, let me do it this way, x squared plus y squared equals 3, let's say. If you took the derivative of this implicitly, what we will have is, 2x plus 2y times the derivative of y. And here we're taking the derivative with respect to x. So here, every time we take a derivative, going back to our problems with related rates, since we're doing them with respect to time t, when we take the derivative, we'll have something of this form. Let's say if I was to take again the derivative of x squared plus y squared equals 3, in terms of t, or with respect to t, what we will have is 2x dx dt plus 2y dy dt equal to 0. So that's exactly what's going to happen on this side. This is supposed to be t, not x. Okay, so now if I take the derivative of the volume function of v equals pi cubed r squared times h, what we have is the following. We're taking this derivative implicitly. So the derivative of v with respect to t is the following. So we're doing the derivative of v with respect to t, and we're taking the derivative on this side of r and h also with respect to t. So let's write it this way. Now be careful here, because here we have a product of two functions. So we have a quadratic and we have a linear. So we will have to use a product rule here when we take this derivative. In any case, the derivative of v is simply dv dt. So dv dt with respect to t is equal to that pi over 3 we could pull out because it's a constant. So we don't have to worry about it. And now we will take the derivative of the inside piece. Now the derivative of this inside piece of r squared times h I will do on this side, just to keep our work clean. So remember the product rule. If you have f times g, that is the first times the derivative of the second plus the second times the derivative of first. So if we let f be r squared and g be h, then that means that f prime is equal to 2r. But remember, because we're taking the derivative with respect to t, we're going to write also dr dt. And for g, the derivative of g, well, the derivative of h is just 1. But again, because we're taking also the derivative with respect to t by the chain rule, we have to multiply by dh dt. Okay, so we have 1 times dh dt, which is simply dh dt. So if we follow this rule, the product rule, we have f times g. Well, f is r squared. So we have r squared times g prime. G prime is dh dt plus g times f prime. Well, g is h and f prime is 2r times dr dt. Okay, now we could clean this up a little bit by simply rewriting or rearranging the multiplication. So we have dv dt is equal to pi over 3 times r squared dh dt plus 2rh times dr dt. Now, from this equation is called the related rate equation. Related rate equation. And from here, we could see that the rate of change, so this dv is the rate of change of the volume with respect to time. This dh is the rate of change of the height of the water with respect to time. And this dr is the rate of change of the radius with respect to time. So we could see that the rate of change of the volume is related to the rate of change of the height and the radius. So note, from the related rate equation, we can see that the rate of change of the volume V is related to the rate of change of the radius R and the height of the water H. Okay, so how could you use this formula up here in a problem? Like if you wanted to work with a concrete problem, how would that work? Well, let's assume that the water tank that I gave you, this blue one, I'll draw it down here. Let's assume that that canonical tank let's assume that the height of the water level is changing at a rate of, so assume the height of the water level is changing at a rate of negative 0.2 foot per minute. And that the radius is changing at a rate of negative 0.1 foot per minute. The question is, what is the rate of change of the volume? So the question that we were interested in answering is, what is the rate of change of the volume when the radius is 1 and the height of the water is 2. And when I say 1, I mean 1 feet and 2 feet. Okay, so we have a formula for this. We could simply use it. So let me just rewrite the formula down here. So the formula that we're working with is dv dt is equal to pi over 3 times r squared times dh dt plus 2rh dr dt. That's from our calculations from above. Now, in this particular problem, I gave us a lot of information. First of all, I gave us the rate of change of the height of the water. I said that that was negative 0.2. Now, the rate of change of the height of the water is represented by the variable, or the expression rather, dH dt. Remember, rate of change of the height of the water, it's the derivative of the height with respect to time. So that's negative 0.2. Now, the rate of change of the radius with respect to time, also from the problem, is negative 0.1. So this is equal to negative 0.1. And finally, the height of the water, we were given it to be 2 feet, and the radius of the tank, we're given it to be S1. So now it's all a matter of plugging into the function. So what we have here is dv dt is equal to pi over 3 times r squared. Well, r is 1, so we have 1 squared times dH dt. dH dt is just minus 0.2 plus 2 times r, which is again, it's 1, h, which is minus 0.2, and times dr dt, which is minus 0.1. Okay, now you don't have to multiply. In fact, I'm not going to multiply the pi over 3 into this, just to keep it clean. But we have pi over 3 times, well, 1 square is 1 times minus 0.2 is simply minus 0.02. And then 2 times 1 is going to be 2, and let's take care of the negative. So we have negative times negative is plus, so it's still going to be a plus. 2 times 0.02 is 0.4 times 0.1. I simply took get rid of the negatives because we have 2 negatives getting multiplied. And now 0.01 times 0.04 is going to be 0.04. So we're going to move the decimal over to the right ones. So we have dv dt is equal to pi over 3 times minus 0.2 plus 0.04. And then if we combine, 0.2 and 0.04, we get dv dt is equal to pi over 3 times negative 0.16. This is why I said I don't want to distribute that pi over 3. This is fine for our purposes. What we could actually find, and this is feet per minute. So make sure you always put the units at the end, because we're dealing with feet and minutes. So this is feet per minute. In any case, we have the rate of change of the volume now. This is an actual number. It is a negative number, so we will see that the volume is decreasing. And that makes sense because the water is being drained. So the less water you have, the lower that volume will be on the inside. So that makes sense. I'm going to end this part right here, and then we'll pick it back up on the part 2 of this lecture with more examples.